Standard normal distribution is a normal distribution with a mean of 0, so mu equals to 0, and a standard deviation of 1, so the sigma equals to 1. And the vertical axis shows the relative frequency, denoted as Fz, and the horizontal line shows the possible values that can be taken in this population, which ranges from -infinity to +infinity. And of course, those extremely small or extremely high, extremely large values are very unlikely to happen, so they have very small Fz's. Because this Fz is relative frequency, so if you give a value, for example, like this -2, and then the corresponding Fz, the F -2, gives you the percentage of the data that has the value of -2. And if you go to this one, you can tell that 24% of the data value is having the value of -1. And because the curve is symmetrical, so there are also 24% of the data that is having the value of +1. And if you examine the area under a number that is under this curve, then that shows the percentage of data points in your population that is below your given value. So because everything is denoted into percentage, and if you sum up every possible values, the Fz for every possible z, then this should sum up to 100%, which is equals to 1. Therefore, the total area under the standard normal distribution is 1. For any normal distribution, they can be transformed to standard normal distribution. And let's see how. So if this x follows a normal distribution with mean of mu and the standard deviation of sigma, then the x minus mu has a mean of 0 and the standard deviation of sigma. Because you shifted every data point to the left with a unit of mu, and therefore the mean will be shifted to the left of mu units. Thus, it has a mean of 0. And because the mean and standard deviation are independent, so the standard deviation still stay at sigma. And now, if you use x minus mu divided by sigma, then every data point is shrinked by sigma times, and therefore the standard deviation will be shrinked to sigma divided by sigma, which is 1. And therefore the x minus mu divided by sigma has a mean of 0 and the standard deviation of 1, right? So now we transform this any normal distribution to a standard normal distribution. And we have this formula. So xi is an individual value that follows a normal distribution with mean of mu and standard deviation of sigma, and the z is the standard normal value. Okay, so you need to use this formula, z equals to xi minus mu divided by sigma, to find the standard normal value. So for example, in the resistance of electrical device example, the mean is 90 and the standard deviation is 2.0. So if you examine this point, 92 as the xi, then the xi equals to 92, which is 90 plus 1 unit of 2, right? Which equals to the mu times 1 unit of sigma. So this is saying that this 92 is 1 standard deviation above the mean. And now if you use this transformation, the standardized normal value for corresponding to xi is xi minus mu divided by sigma, 92 minus 90 divided by 2, which is plus 1, right? So if you interpret this z in the standard normal curve, then that means this z is also 1 standard deviation above the mean, right? So because we use relative frequency on the vertical axis, so if the xi and z are corresponds to each other, then the area below z and the area below xi are actually the same. The area under the normal curve is a very useful statistic. It shows the percentage of population below a given value. So we want to first show how to find the area under the normal curve for standard normal distribution. So how to compute this area? There are two ways. First, you can use calculus. So this is the integration formula that you need to use. Not quite a big fan of the calculus. Then you can go to the Appendix A, Table A, which actually records the area under the normal curve for standard normal distribution. So that can help you release some of the efforts in computation. Okay. So as you can see, given a value z in the standard normal distribution, this shaded area shows the area under the curve for z, right? And it's just the same as the percentage of population below z. So let's have a look at the table A, the areas under the normal curve. And I'm going to tell you how to look up the values in this table. So the first column shows the z value that has one digit after the decimal point. And the first row stands for the second digit after the decimal point. So you need to combine these two together to define a z, and then to use this column and the row to identify the area under z. Okay, so for example, I want you to find the area under the standard normal curve for z equals to minus 3.16. So you need to first define this z in the table, which is minus 3.1. This 1 is the first digit after the decimal point, and then this 6 is the second digit after the decimal point. So this column and this row locate this value. This value is 0.00079, which is the area under the normal curve for z equals to minus 3.16. So now, what if I want to know the area under the normal curve for any normal distribution? If you go with the calculus, then you will find an even messier integration than the standard normal distribution. So now we can use the equivalency between any normal distribution and the standard normal distribution. If you view the vertical axis as the relative frequency, then that is just a percentage. And now the area under xi in the normal distribution with mean of mu and the standard deviation of sigma is equivalent to the area under this z in the standard normal distribution. So how to find the area under the normal curve for xi? Then in the step 1, you need to first standardize xi to z using this formula that we have talked about before. So z equals to the xi minus mu divided by sigma. And this mu and sigma is the population mean and standard deviation associated with the xi's distribution. Okay. And step 2 is to look up this table A for the area under the standard normal curve for z. So now you do not need to involve with any calculus or integration.